Okay, so in this video, we are going to be discussing the first of our selection of gas laws. So we are going to be looking at the combined gas law and then also Dalton's law of partial pressure. But before we get into the details of that, we need to talk about which particular variables can be analyzed and discussed in reference to gases. So there are four quantities that we can look at and discuss when we are talking about gases and the particular characteristics of a gas. So the first one is the quantity of that gas in moles. For gas laws, when we are talking about moles, we use the variable, the lowercase n, and you can come by the moles multiple different ways. Any of those methods that we use during the stoichiometry unit to get moles are means of getting moles in this unit as well. Okay, so then the second one is temperature. With gases, when we are discussing temperature, temperature is always discussed in Kelvin. So to get the Kelvin temperature, you take your Celsius temperature and you add 273. We need the volume of the gas in liters, and that is represented by the variable V. And then the pressure of the gas, pressure in the capital T. Let me scoot it over so we can actually see, in the capital P. And there are multiple appropriate units of pressure that can be used. We have atmospheres, millimeters of mercury, kilopascals, torrs, and pounds per square inch. And given that there are so many different units of pressure, it's important to realize that you are able to convert back and forth between these units. And that's something that we're getting ready to look at right now. So how to convert between units. Now, the reason why we're going to need to be able to convert between units is as we were working our way specifically through the combined gas law, if you were doing a problem that has more than one pressure unit, in order for your units to cancel out, for things to work out mathematically appropriately, they have to be in the same pressure unit. So if you have one measurement that's, say, for example, in atmospheres, and the other one is in torrs, we have to make a match. So you have to understand how to convert between your pressure units, which is just an application of what we learned with unit conversions and stoichiometry. So the first thing that we need to understand is all of our standard pressure units are equal. And therefore, we can use them as conversion factors. These are on your reference packet. So let me grab a reference packet. If you look in the box right underneath where we find Avogadro's number, we have a section that's listed as gas constant. Right below that, we have our section of standard pressure. So they are on the reference packet. And we can use those as conversions. And so all of these things are equal to one another. And I've added the one at the end, pounds per square inch, that's not on your reference packet, but is useful information. So 1.00 atmospheres is equivalent to 760 millimeters of mercury, is equivalent to 760 torr, to 101.3 kilopascals or kPa, and 14.7 pounds per square inch. All right, so we're just going to run through a couple quick examples of these conversions. And this is, again, just like what we saw in stoichiometry. Whatever unit you're getting rid of, we would put on the bottom of our conversion factor, and whichever unit we're going to would go on the top. So in this case, we have 1.5 atmospheres, and we are being asked to find millimeters of mercury. So I would set it up just like a regular conversion. 1.5 ATM times, and then I'm going to write in my conversion factor. I'm getting rid of atmospheres, so atmospheres goes on the bottom. I'm going to millimeters of mercury go on top. So then I look at my conversion factors. 760 millimeters of mercury is equivalent to 1.00 ATM. My atmospheres are going to cancel, and that's going to leave me in millimeters of mercury. So let's see, 1.5 times 760, and then the divided by 1 is rather unnecessary. 1140. All right, and then remember, consider your sig figs. All of these are conversion factors. They are all constants, so I can only look at the number of sig figs I had going in. So 1.5 went in, that's 2 sig figs, so 2 can come out. This would be 1100 millimeters of mercury. All right, so pretty standard. All right, for the next one, 95 kPa to torr. So again, setting it up the same way, 95 kPa times, I'm going to get rid of kPa, so kPa goes on the bottom. I'm going to torr goes on top. 760 torr is equivalent to 101.3 kPa, so 95 times 760 divided by 101.3, that comes out to 712.7. 2 sig figs go in, so 2 can come out. So what, 710 torr. All right. And our last example. So 435 kPa, kilopascals to pascals. Now this one, notice that my unit has stayed the same. So it's not a conversion that I would look for up here. This is going from kilopascals to pascals. So this is actually just a metric conversion. So remember, with our metric conversions, this is no different than going from kilograms to grams or kilometers to meters. You need to remember your metric prefixes, your metric arrangement. So remember that kilo is a large prefix, hecto, deca, your base unit, deci, centi, milli. So from the base, this is 3 up, 10 to the third. So when I'm looking at this, I know that there are 1,000 PA in 1 kPa, and all I've got to do there is multiply. So that gives me 435,000 PA. Stayed in the same unit, I just did a metric conversion. All right, so these skills that we just reviewed here, you will need as you go through and work. Like I said, in particular, the combined gas law, you see this a little bit more often. But anytime you are asked to convert pressure units, it is a particularly helpful skill to have. All right, so let's go to the next part. So the combined gas law. The combined gas law is a, obviously, combination, hence the name, of 3 separate gas laws. Those 3 gas laws are Boyle's Law, Charles' Law, and Gay-Lussac. And instead of having to learn 3 individual formulas, what we're going to be using is the combined gas law. The combined gas law puts together all 3 of those gas laws into one, and then we can just add and remove the particular variables that we need at a given time. So this is the way that you see the combined gas law on your reference packet. Pressure 1 times volume 1 divided by temperature 1 equal to pressure 2, volume 2, and temperature 2. And this is the standard way, but pretty much no one uses it that way. Almost everyone is going to multiply your T1 and T2 across and end up with this more linear arrangement. It's just a little bit easier to work with. And you know that, like, for example, if I needed to solve for V1, I would divide the other side by P1 and T2. If I needed to solve for P2, I'd divide this side by V2 and T1. It just makes it a little bit easier to get this fraction part out of the way. So the combined gas law allows you to analyze different properties of a sample of a gas under different conditions. Kind of think about this like before and after. So you have a sample of a gas at a specific pressure, volume, and temperature, and then I'm going to see at what temperature or pressure or volume would that exist if I changed the other 2 scenarios. But it's the same sample. It's just the same sample at different conditions. And the before and after values of that sample have to be equal. Whatever the combined characteristics of that sample was at the beginning has to equal what it is at the end. I might adjust the values, but they all have to work together to combine to make the same numerical value, is what the combined gas law is actually telling me. So you need to think about it as a before and after, and all the changes that you have should make good logical sense if you understand the individual components of that combined gas law. So let's go through those individual components. So the first one is Boyle's. So Boyle's law specifically deals with the relationship between pressure and volume. And we talked a little bit about this when we were doing Le Chatelier's principle in our equilibrium unit. We talked about how you could talk about pressure or volume for gases, and it really meant the same thing because of the relationship between pressure and volume for gases. So Boyle's law tells me that pressure and volume are inverse at a constant temperature, meaning that if pressure goes up, volume goes down, or if pressure goes down, volume goes up, that they are opposites. And the example I did at that time was if I had a soda bottle and it was sealed and I squeezed it, that would be increasing the pressure, but the inside of my soda bottle would have gotten smaller, so that was decreasing the volume. And then if I could stretch that soda bottle out really large, that would be lowering the pressure because now the molecules have more space to move around in. So that's your Boyle's law. The second one, Charles' law. Charles' law is volume and temperature are directly proportional at constant pressure. So if my temperature goes up, my volume's going to go up. If my temperature goes down, my volume's going to go down. So if you think about it, remember that temperature is a measurement of kinetic energy. If I slow down the molecules, i.e., if I reduce the temperature and my molecules slow down, wouldn't it kind of make sense that they're going to condense? Think about your phase changes. If I've got gas particles like water vapor and I slow them down, don't they come closer together and condense into liquid water? So as I reduce the temperature, I decrease the volume. Okay. And then finally, Gay-Lussac is the relationship between pressure and temperature. And the fact that pressure and temperature are directly proportional at a constant volume. And so think about it that if I increase the temperature, therefore increasing the kinetic energy, won't my molecules be banging into the walls of the container more aggressively? Well, those collisions are what give us the pressure. So increasing the temperature would absolutely increase the pressure. So instead of having to learn an equation for this, an equation for this, an equation for this, we instead have our combined gas law. But it's still really important that you know which variables correspond to which law. So the easiest way to do that is if you think about these in alphabetical order, which is how I list them, then you look at your equation in the linear form, you can use a little trick to know who is who. So if we take them in alphabetical order, Boyle's law are my first two variables, pressure and volume. Charles' law is my second set of two variables, volume and temperature, and Gay-Lussac are my two outside. Okay, so that's how I remembered them. So the first two, pressure and volume, Boyle's. The second two, volume and temperature, Charles, and the outsides are pressure and temperature, which is Gay-Lussac. Okay, that might be helpful on your test. All right, so we're going to do some sample problems. Before we jump into the sample problems, there's two important points that you need to make sure that you remember. First, STP. We've talked about STP, this abbreviation before, that it stands for standard temperature and pressure. And this was the thing in our stoichiometry unit that allowed us to use the relationship that 1 mole of a gas is equal to 22.4 liters. Well, as we are calculating gas laws, STP is also helpful for other reasons. If a question says, well, the gas at STP does X, Y, and Z, what that's telling you is, oh yeah, the temperature is 270 Kelvin and the pressure is 1 atmosphere, or any of those equivalent standard pressures would also work as well. And so that's just kind of, if I say STP, the expectation is you know what that means. You know what numbers you can plug in there. So anytime you see STP, 273 is your temperature and 1 atmosphere or one of those equivalent are able to be used for the pressure. Always, by just side note, always default to 1 atmosphere unless told otherwise. Makes your math a lot easier if you're just multiplying and or dividing by 1. The second thing is for all your gas law problems, whether they be combined, whether they be Dalton, whether they be ideal gas law, which we'll get to later on, you have to be in Kelvin, period. Okay. Even if the question gives you a Celsius temperature and asks for a Celsius temperature, you have to do the problem in Kelvin and then convert back. You'll be wrong if you don't. So 273 plus your Celsius temperature gives you your Kelvin temperature. You must convert to Kelvin. That is one of the more common mistakes in the gas law unit, is failing to remember to convert to Kelvin. All right, so let's just jump into a problem. So gas law problems are not hard. It is a lot of plug and chug math. Generally, the issue that students have is that they plug and chug into the wrong spots. So I'm going to show you the kind of hints and tips that I use to keep myself straight, and then I would recommend doing those things as well. So I'm going to grab two different color pens. You'll see why here in just a second, in addition to my black pen. So let's look at our scenario. What is the volume of a gas at 303 Kelvin and 2.5 atmospheres if the volume at 1.5 atmospheres and 20 degrees Celsius is 3 liters? There's a lot of data points there. So I know, because I have two of a unit, I have two temperatures, I have two pressures, that this has to be a combined gas law problem. So the first thing I'm going to do is make a list. P1, V1, T1. P2, V2, T2. And this is going to allow me to first organize my data and also keep track of it so I don't plug something in wrong. So I'm going to run through my problem, and I'm going to circle the variables that go together. And it doesn't matter if the first set of variables I have, I put as the ones, or if I put them as the twos, as long as they're paired together, it really does not matter. So what is the volume? Well, that's what I'm looking for, of a gas at 303 Kelvin and 2.5 atmospheres. All right, so I'm going to fill in those in my list. So my pressure, 2.5 atmospheres. My volume is what I don't know. My temperature is 303 Kelvin. All right. If its volume at 1.5 atmospheres and 20 degrees Celsius is 3 liters. All right, 1.5 atmospheres, 20 degrees Celsius, and 3.0 liters. All right, there are all my variables. So I have a before and after scenario, and now I'm going to plug this all into the combined gas law. But what's the thing I need to do first? For all gas law problems, temperature must be in Kelvin. So I'm going to add 273 to this Celsius temperature. That's going to give me 293 Kelvin. My pressure units match, so I don't have to worry about converting. If one of these was different, I would have to make them the same. It wouldn't matter what I made them. Say, for example, this was atmospheres and this one was torr. I could pick either. They just have to be the same so my units cancel out. My temperature is fine, and my volume, this is in liters, so that means that's going to come out in liters. All right, so P1, V1, T2 equals P2, V2, T1. I'm solving for V1, so I'm going to divide by P1 and T2. All right, and then now literally I'm just going to go down my lists. I'm going to make sure I plug in right. The biggest thing people miss with this is they put their temperature in the wrong place. So that's why these lists are kind of helpful. All right, P2, 1.5 atmospheres times V2, 3.0 liters times T1, make sure you go to the right list, 303 Kelvin, divided by P1, 2.5 atmospheres, and T2, 293 Kelvin. All right, so we go to our calculator. 1.5 times 3.0 times 303, get an answer, divided by 2.5 times 293. And that gives me 1.861. All right, now let's check our sig figs. 2, looks like 2. All right, so 1.9 liters. And in this particular problem, I didn't give you a specific substance. It just says gas. So I left it generic. So 1.9 liters is fine. If I had given you a substance up here, say, for example, I had said it was oxygen, you would need to give me a substance. A good rule of thumb is if a substance is given, give one back. In this case, one was not given, so you're good to go. All right, let's look at the next one. If a gas has a volume of 2.5 liters at 22 degrees Celsius and a pressure of 600 millimeters of mercury, what's the temperature of the gas at 1 atmosphere and 1.8 liters? Okay, So let's see. I should probably make a list again. P1, V1, T1, P2, V2, T2. All right, let's read through the problem. Again, if a gas has a volume of 2.5 liters at 22 degrees Celsius and 600 millimeters of mercury. All right, so 600 millimeters, 2.5 liters, 22 degrees Celsius. What is the temperature, so I'm finding T2, of the gas at 1.0 atmospheres and 1.8 liters? Okay, so let's look and see if we need to do any converting before we start. I've got 600 millimeters of mercury and I've got 1 atmosphere. I've got to make them the same. Now, I could go and take my millimeters of mercury here and make it atmospheres, or I can take my atmospheres and make it in millimeters of mercury. It doesn't matter which one I do. I'm going to get the same answer either way, but one of these is easier than the other. So think about it. For this one, I'm going to have to divide this by 760. Absolutely, am I going to need my calculator for that? For this one, I would be multiplying by 760 over 1. Well, heck, I can do that in my head. 1 times 760 is just 760. So if I can not have to use the calculator and make it less likely I screw something up in it, that's what I'm going to do. So I'm converting to millimeters of mercury. All right, liters and liters, I'm good. Oh, degrees Celsius. Got to make this Kelvin. So plus 273, that's going to give me 295. Okay, looks like I'm ready to rearrange and plug in here. P1, V1, T2 equals P2, V2, T1. I'm solving for T2, so that means I'm going to divide by P1 and V1. Get rid of that. All right, T2 equals, let's see, P2, well, I changed it, so it's 760 times V2, 1.8, times T1, 295, over P1, 600, and V1, 2.5. All right. So 760 times 1.8 times 295 divided by 600 times 2.5. 269.04. All right, so let's look at the question. It asks for the temperature, but notice how it doesn't specify a unit. I started off here in Celsius. I had to convert to Kelvin for the problem. If it doesn't tell me what unit it wants me to give it back in, I'm leaving it in Kelvin, okay? If it says specifically convert to Celsius, then I would subtract 273 and get a Celsius temperature, but it doesn't tell me to do that here. Why do extra work when it's not requested? So if it doesn't say, you are free to leave it in Kelvin. So let's check our sig figs. Well, it looks like I can have 2. So we're going to go with 2, and that's going to be 270 Kelvin. All right, easy enough there. So we're going to do one more combined gas law. In this particular one, I'm going to illustrate something that's pretty darn helpful for future combined gas law problems. All right, so let's read through this and then see if you can figure out what I'm getting ready to show you. What will be the volume of a gas at 409 Kelvin if its volume at 215 Kelvin is 4.6 liters? Seems like I don't have a bunch of variables this time, right? I don't have a bunch of data. What am I missing? It didn't say anything about pressure. So what do I do with that? Well, you have some choices. It didn't say anything about pressure. So the only thing that I can do is assume, well, the pressure must not have changed, because if it did, they would have told me. So if the pressure didn't change, I can just ignore it, right? Because if it's a numerical value that did not change, mathematically, aren't I just going to be multiplying and then dividing by the same number? So I can just leave it out. If that freaks you out, by all means, plug something in, but be smart about it. Plug in 1 atmosphere. Make the math easy. But if something's not mentioned in the whole problem, That means it's constant. So if you have a problem where all you're given is volume and pressure and no temperature, well, then the temperature must have been constant. If you're given just pressure and temperature, well, the volume must have been constant. So if it's not mentioned, you need to read between the lines and realize, oh, it didn't change. It's constant. Oh, I can leave it out. Way to make my life easier. All right. What will be the volume of a gas at 409 if its volume at 215 is 4.6 liters? All right. Nothing is said about pressure, so I'm leaving it out. All right. P1 V1 T2 equals P2 V2 T1. And then just like I did here, cross out that pressure. All right. All right. What am I solving for? V1. So I'm going to divide this side by T2. All right. V1 is equal to V2, 4.6 times T1, 409, divided by T2, 215. 406 times, or 4.6 times 409, divided by 215. All right, 8.5 or 8.75. Looks like I can have two sig figs. I'm going to call that 8.8 liters. All right, so we're going to stop here in terms of combined gas law because they're all the same, right? Identify the variables. What's your ones? What are your twos? What are you solving for? Rearrange, plug in, and solve. Make sure in terms of your show work, you at least show me this, right? If you want to go without doing the chart, that's up to you, but I'm not giving you credit for your homework if you don't have at least this. Show me how the numbers are plugged in. All right, so now we're going to go on to the second part of our lesson on combined gas laws today. Or I'm sorry, gas laws. We just did combined gas laws, which is Dalton's law of partial pressure. So with Dalton's law of partial pressure, we've got two applications of Dalton's law. So the first one is the more common one. The pressure of a mixture of the gases is the sum of the partial pressures or the individual pressures of the gases. So that means that the total pressure is equal to the pressure of gas number 1 plus the pressure of gas number 2 plus the pressure of gas number 3. All right, that makes sense. Add them up. Cool. The second application draws from this, but then adds a little bit more. So for example, if most of my gas was gas number 1, it's the most represented. It's the pressure that should be most prominent. And that leads me to a second equation. The partial pressure of each gas in a mixture depends upon the number of moles of that gas, which we call the mole fraction, or the percentage of that gas in a mixture. Meaning, if the gas is highly represented, it should be a bigger part of the total pressure. If the gas is only marginally or slightly represented, it should only be a small part. It makes sense, right? But it's helpful to see an actual equation for it. So the pressure of gas 1 is equal to the fraction of that gas or the percent of that gas times the total pressure. All right, so we're going to do 4 examples of Dalton. All right, first one. If the gases in a mixture have the following partial pressures, what's the total pressure? So we've got oxygen at 735 millimeters of mercury, nitrogen at 45 millimeters of mercury, and carbon monoxide at 523 millimeters of mercury. I've got individual pressures. I've got a mixture of gases. I just have to add these up, right? Add them up, add them up, add them up. That's all I got to do. So let's add them up. The pressure total is equal to 735 plus 45 plus 523. Now, all of these are already millimeters of mercury, so I don't have to do any conversion. If they were different units, I'd have to convert and make them all the same, but they're all the same already, so we're good to go there. Yeah, I added them up. 1303 millimeters of mercury. Seems easy. It is easy, right? And remember, we're adding and subtracting, so addition and subtraction rules are decimal places. All of these are whole numbers. I got a whole number. All right, easy peasy. Let's go down the next one. If the total pressure of a mixture of oxygen and nitrogen is 1,540 millimeters of mercury, what is the pressure of the nitrogen if the oxygen is 675? Well, instead of all of the parts, I have a whole and one part, and I'm asked to find the missing part. It seems like I'm subtracting, right? Yeah. 1,540 millimeters of mercury is the total, minus the one part I have, 675. That's going to give me my missing piece. 1,540 minus 675. All right, so that's going to be 865. And I do know that this is the nitrogen. So I'm going to put the substance on there because I know that that's what it is. Well, those two were pretty easy. All right, let's see what the next one is. If the atmospheric pressure is 592 millimeters of mercury, what is the pressure of the nitrogen if it is 63% of the gas? Oh, okay. So the pressure of the nitrogen is equal to the fraction of the nitrogen times the total pressure. I have the total and I have the percentage, which is my fraction, so I can just solve. Pressure of the nitrogen is equal to 0.63 times 592 millimeters of mercury. So 0.63 times 592, 372.96 to 2 sig figs. 370 millimeters of mercury is the pressure of the N2. Okay, well, that wasn't hard. Let's see what the last one says. If O2 makes up 27% of a gas and has a partial pressure of 136 millimeters of mercury, what's the total pressure? All right, so this time I have the partial and the percent, I'm finding the total. So if up here I was finding the partial and I multiplied, if I'm finding the total, aren't I just dividing? Yeah. So the pressure of the oxygen is equal to the fraction of the oxygen times the total. 136 is equal to 0.27 times the pressure of the total. So 136 divided by 0.27, 503.7 is my total pressure. All right, check my sig figs, 2. So 500 to 2 sig figs is going to be 5.0 times 10 to the second millimeters of mercury. And then, does that make sense? Well, oxygen is less than 30% of the total. So yeah, that should make sense. My total pressure should be much more than my partial. Yeah, that makes sense. So make sure that your answers make good logical sense. Now, I happen to just pick on millimeters of mercury here. You could do this with other units too. It just happens to be that that's what I picked on when I wrote these examples. All right, go forth, solve gas law problems.